I'm Ian Somerville, and in this video I'm going to be talking about system safety and introducing some of the terminology around safety critical systems. As computer-based systems have become a ubiquitous part of everyday life and work, it's inevitable that these systems have been used in areas where failure of the system can cause injury or damage to people or property. Hence, we need to think about the safety of these systems. And safety is a property of the system that reflects the system's ability to operate without causing damage or injury to people, property or the environment. Recall that safety is one of the four principal dependability properties: availability, reliability, safety and security, with the relationships between all of these properties. And I'll be talking here about the relationships particularly between reliability and safety. When a system is used in an application where there is the potential to cause injury, we call this a safety critical systems, sometimes called a safety related system. And there are two classes of safety critical system. They're what you can think of as primary safety critical systems. These are systems where system failure can result directly in injury or death to some person. An example of such a system is a radiation therapy machine, which is used in hospitals to deliver radiation to kill tumours in people suffering from cancer. It's a software controlled machine, and if things go wrong, an overdose of radiation or an underdose of radiation can be delivered, and this can injure the patient. This is a picture of such a machine. It wasn't this machine, but a different kind of radiation therapy machine went wrong some years ago. Overdoses of radiation were delivered and several patients were killed. The other class of safety critical systems are what you might call secondary safety critical systems. And these are systems where failure does not result directly in injury or death, but there can be consequent injury caused because of that failure. One example of such a system is a medical record system. If a medical record is corrupted or incorrect, this means that clinicians can make the wrong decisions about treatment, and these can injure the patient. Another example would be a CAD system used for aircraft or car design. If that went wrong, we could have cars or aircraft with parts that are of the incorrect specification, and failure of these parts could cause injury or death. If we get our system specification right, and obviously we try and avoid all safety related problems in the specification, and that specification is properly implemented, then you might think that reliable operation means safe operation. Well, reliability is certainly essential for safety, and this is the kind of default, obviously, that we need to get things right. But we have to allow for the possibility that a reliable system can be unsafe. Reliability in practice is about delivering a system that conforms to its specification. Safety is about delivering a system that is always safe, irrespective of whether or not it conforms to its specification. And the issue which we have to address when building safe systems is the possibility that the specification will be incomplete or incorrect. It's perfectly possible for a system that's reliable and certified as reliable to be unsafe. And this is an example of an aircraft accident that happened at Warsaw Airport some years ago, where a system behaved reliably according to its specification, but failed to apply the brakes on the aircraft properly, and so it ran off the end of the runway. I'll be covering this in a separate video. There are a number of reasons why systems that seem to be reliable may be unsafe. First of all, it's possible that there are dormant faults in the system that our reliability testing have not exposed, and these may come to light in exceptional circumstances and cause problems. It's also possible that there may be specification errors or misunderstandings, so that the system implemented does not reflect the practical requirements of the system's operational environment. When hardware goes wrong, it sometimes produces very strange signal patterns. So a failing hardware component can produce patterns which are way outside of our specification and which can cause equipment to go wrong as a consequence. And we have the common possibility of operators issuing the right commands at the wrong time. There's an apocryphal example of an aircraft technician who was working in an aircraft cockpit and pressed the button to raise the undercarriage. The aircraft was on the ground at the time, but the software still tried to raise the undercarriage. Obviously it failed to do so, but it did quite a lot of damage to the aircraft. When we talk about safety, in the same way as we use specialised terminology in reliability, there are three terms that are quite important to understand. One is an accident. That's when something actually goes wrong and causes damage or injures people. A precursor to an accident is something that happens in the system. It's something that happens in an executing system. It's what's called a hazard. It's a state of the system that has a potential to cause an accident. It doesn't follow that it necessarily will cause an accident in the same way as errors in the state do not necessarily cause system failures, but it has the potential to cause an accident. So a hazard is something that is potentially dangerous. And the damage that's done in the event of an accident is a measure of the extent of the injury or loss that accrues. Now, when we're building safety critical systems, there are three approaches that we can adopt. We can adopt the approach of hazard avoidance, where we design and build the systems so that hazards simply cannot occur. To give an example of this from a non-software domain, if you have a mechanical paper guillotine that's used by an operator, have two buttons to operate the guillotine. Then there's no way that the operator's hands can be in the paper path. Hazard detection and removal is where we incorporate checks in the system that look for the hazardous states that might arise, and if they're detected, we ensure that these are corrected before they result in an accident. And damage limitation is where we accept the possibility that accidents may well occur, but we put in protection features so that it's possible to recover from that accident and minimise the practical amount of damage that can occur. So a very simple example would be a backup system. That's a protection system that allows us to recover from an incident. Obviously this isn't a safety critical system. In summary then, safety is a property that reflects a system's ability to operate without causing injury or damage to property of the system's environment. Safety and reliability are closely related, and achieving reliability is a necessary but not a sufficient condition for achieving safety. It's possible for systems to be reliable but unsafe, primarily because of specification errors and misunderstandings. Hazards are conditions that may lead to an accident, although it's not necessarily the case that they will do so. And we achieve safety through hazard avoidance, hazard detection and elimination, and damage limitation. You can download the slides that accompany this video from my SlideShare account.